Oh, it's working now. Good morning, everyone. My name is Jin-Young Jeong. I'm from Seoul National University, South Korea. I'm very excited to share my research with you today. I'm going to talk about is best relaxation water really a pre-water? My talk will cover what is the best relaxation water and the microscopic original best relaxation water. This is my contents. Let me introduce what is the best relaxation water and previous studies on best relaxation water. And I will present my work on understanding using dielectric spectroscopy and molecular dynamic simulations. Water molecules have many different dynamics in gigahertz to terahertz and infrared region. So water molecules rotate in gigahertz and terahertz region, and it has stretching and vibration mode in infrared region. We are interested in the rotational motion of water in gigahertz and terahertz region because it is very important. Rotational motion is related with the biochemical reactions like proton and electron transfer. Water molecules reoriented in the hydrogen bond network in the time scale of picosecond. As you can see in the picture, rotation of water molecules in the course of switching hydrogen bond causes the reorientation of water dipoles. Debye proposed dielectric relaxation model to describe this reorientation of motion. He described the water molecules as a spherical dipole. When the field is applied, the dipole is aligned in the field direction. And after the field is turned off, the polarization will be relaxed as a rotational diffusion. He assumed 3 points. There is no interaction between water molecules and random motion by collision and small step diffusion. From Clausius-Moses relation, Debye derived the relaxation model. So we can describe this reorientation of motion with dielectric strength and relaxation time. Debye model was a success. Dielectric constants of liquid water is well described by Debye model below 100 gigahertz, like this. So the relaxation time of collective reorientation is estimated as 8 picosecond. However, it was found that the Debye model doesn't fit well at terahertz frequency. As you can see here, there is a small deviation from the model and experiment result. So as you can see here, the Debye model does not fit well at terahertz result. Therefore, adding one more term to Debye model, so-called double Debye, fits very well with measurement at the terahertz region. So double Debye model looks like this, and people call this as a slow relaxation water in the gigahertz region and fast relaxation water in the terahertz region. This small tiny thing in terahertz region attracts many researchers' interest. So naturally, one question arises: what is the microscopic original best relaxation water? At the first time, people think best relaxation mode was thought to be originated from the hydrogen bond because best relaxation time, about 1 picosecond, is very close to the hydrogen bond lifetime. And the activation energy of this relaxation mode is very almost same as the hydrogen bond energy. So at the first time, people think this mode is originated from the hydrogen bond. After that, best relaxation water is considered to originate from the pre-water. Tanaka group compared the collision time of supercritical water, which is composed of pre-waters, and the best relaxation time. This is the collision time of the pre-water, and the black circle and black triangle is the best relaxation time. So relaxation time is very well agree with collision of pre-water. So people think best relaxation water is originated from the pre-water or weakly hydrogen bonded water. And interval rotation relaxation can be considered as the origin of fast relaxation water. Water molecules remain in quasi-equilibrium state on the duration of waiting period between jump from hydrogen bond to another bond. So during this jump, the water molecules slightly vibrate, like interval relaxation. Recently, scattering measurement like Raman and neutron scattering also observed the fast relaxation mode in THz region. So from this scattering measurement, people think fast relaxation mode is coming from the structural relaxation of hydrogen bond of individual molecules. This is the previous result of our laboratory. We observed that the fast relaxation water is strongly correlated with membrane distance. We use membrane multilamellar vesicles as a platform of the experiment, and we compared the dielectric spectroscopy with small angle X-ray scattering. As you see here, the fast relaxation water is increased as the salt solution, and surprisingly, at the same time, the repeat distance of membrane is also increased with the salt concentration. What I want to emphasize here is why the fast relaxation water is increased with the salt solution. So to answer this question, we select the ion as a sample, since the ions change the hydrogen bond. Ions are known to having structure breaking and structure making impact. So therefore, we use ions to perturb the hydrogen bond structure to see the relation between fast relaxation mode and hydrogen bond structure. This is our experimental setup. We use vector network analyzer with open-ended coaxial probe from 5 to 30 GHz at 25 Celsius degree, and THz TDS with attenuated toral reflection prism from 0.3 to 1.2 THz. And we also conduct molecular dynamic simulation. Molecular dynamic simulation is tool for seeing microscopic hydrogen bond structure of water. Dielectric spectroscopy can only see the macroscopic behavior of water, but molecular dynamic simulation can see the microscopic nature of the system. So we use this simulation to compare, to see the relationship between hydrogen bond structure and rotational dynamics. This is our experimental result. The change of dielectric constants by salt solution is observed like this. The permittivity and dielectric loss is changed by salt solution. So we decompose the dielectric constant with Debye model. Here we use triple Debye model. The black dot is the raw data, and the first mode is collective reorientation of water at 8 picosecond, and the second one is we are interested in. So from now on, I call this mode as a fast relaxation. And the last one is coming from the vibrational relaxation of hydrogen bond. This is the relaxation time of 3 mode, and this is the dielectric strength of 3 mode. It was observed that the fast relaxation water is increased with the sodium chloride concentration. This red square is the dielectric strength of fast relaxation mode. So this mode is increased with the NaCl concentration. This is the MD simulation result. This is the number of hydrogen bond distribution, and these columns are distribution of free water without hydrogen bond, and these columns are for hydrogen water molecules having 1 hydrogen bond. As you can see here, the free water and water molecules have 1 hydrogen bond is increases as the salt solution, salt concentration. So we compare the simulation and experimental result. Here you can see the potassium chloride and sodium chloride. The blue line is the water molecules have one or zero hydrogen bond, and the red one is fast relaxation water from the experiment. So as you can see here, there is a strong correlation. So the coincidence of increasing tendency between the fast relaxation water and water molecules having one or zero hydrogen bond is observed. So from this strong correlation, we can say that the fast relaxation water is originated from the free water or one hydrogen bonded water. So to answer this phenomena, we analyze the ND simulation data. This is a radial distribution function. Radial distribution function is defined as the local density of molecules. This is the radial distribution function of KCl and NaCl. There is a first peak and second peak here. The first peak means the nearest distance between the water molecules, and the second peak is related with the hydrogen bond network. As you can see here, the shape of second peak is collapsed with the salt concentration. This means a hydrogen bond network is broken when the ions are added. And we also analyze the hydrogen bond length and strength. The hydrogen bond length is increased as the salt concentration. This lengthening of hydrogen bond means hydrogen bond length is hydrogen bond strength is weakened. From this result, we can say that when the ions are added, the structure of the water network is broken or weakened, and the result of the structure breaking, the fast relaxation mode is increased as the salt concentration. Let me briefly summarize my talk. To investigate fast relaxation water from relaxation dynamics, we conduct microwave to terahertz directed relaxation spectroscopy and simulation. This simulation shows the fast relaxation water is originated from the water with 0.11 hydrogen bond. The further study is underway by quantum molecular dynamics simulation. This is end of my talk. Thank you.
Thank you very much. We have time for a few questions.
So just going back to when you get into the higher frequencies, the terahertz frequencies, where that's, like you said, is likely to be more vibrational in nature. As you add the ions, and as you also said, you weaken the hydrogen bond strength, you're going to have a few things going on, right? So you're going to have, because of that weakened strength, you'll have the vibrational peaks or density say shift to lower frequencies because of the weakened bond. But then you also see the increase in intensity that could come because now you have more charge, so you have a larger changing dipole. So any way of decoupling these things, or how do you interpret what's, instead of saying at this frequency there's a change in the dielectric strength, but what is it actually coming from? Is it coming from a shift? Is it coming from an increased coupling to the dipoles?
As you mean the dielectric constant is slightly shifted to the high frequency?
Well, especially when you showed it as a function of, like this, but yeah.
So I think this shift is coming from the weakening of hydrogen bond. So hydrogen bond is weakened by ions, and as a result of weakening, the relaxation dynamics is faster than normal state.
One more question?
Yeah. I'm wondering, when you talk about the structure of water, does that mean the H2O molecule actually have some ordering in the water instead of disorder distributed?
Say again, please. Sorry.
The molecule H2O in water, there is some structure ordering in the water or disorder. Since you talk about the structure of water.
Water structure means there is a hydrogen bond network around the water. So it is made of hydrogen bonds.
I think he asked if there is some crystalline areas in water. I mean, this old iceberg model assumes that you have structured water and amorphous water around.
Yeah, to a short distance.
Yeah,
Local or
May I also? I have to admit that I personally don't like the double Debye and triple Debye model. When Debye developed his model, he had a clear picture what he meant, what every parameter in his model means. But then if you go to the double Debye model or triple Debye model, you're not only introducing a new time constant, where you then can guess what it means, it could be this relaxation, but you also are introducing S2 and S3. My question to you is, what's the meaning of S2 and S3? What's the physical meaning? It's a fit parameter, right?
I think we should start from the assumption of the Debye. So at the first time, Debye assumed there's no interaction between particles, and he assumed there is a one friction coefficient and one relaxation time. So I think there's a water molecules have varying number of hydrogen bonds from 0 to 6. So original Debye model cannot explain this variation of hydrogen bond. So in real system, there's a water molecules varying numbers of hydrogen bond. So I think.
Maybe one more comment. I'm not surprised that the original Debye model with just one term cannot explain it, because if I'm not mistaken, I may be wrong here, but I think Debye developed it such that one assumption was that all these relaxation are much, much faster than the electric field oscillation. And if we come to the Terz range, the Terz field oscillates really quite fast, and that's on the order of this relaxation time. And that means that you cannot use the Debye model because an important assumption does not hold anymore. At least that's my understanding. And therefore, you have to, it's not surprising, and then you come up with double and triple Debye models, but in my view, it's just fitting models. Right? So I personally, it's maybe my personal problem that I don't like this too much.
Okay, thank you for this question. I think in the interest of time, we should probably move on because we're running a little bit late. So thank you again for the very nice talk. So the next talk is